Welcome back, everybody. Hope everyone had a good week. Couple of things. Remember, today we had the midterm lab. I also forgot to account for the spring break, which is not next Friday, but the Friday after. So I had to adjust some assignments, push them up. So you'll see, probably get some alerts. Assignments have been changed. Obviously, you can get an assignment during spring break. So I moved things around, but you still have plenty of space in between chapters and so forth. Also open today and ends tomorrow is exam number 2. So don't forget that. So you got 2 exams this weekend to work on. You have any questions about any of that? Everyone understands what's due today? No. But if you do, feel free to send me an email. I'll be keeping a close watch on my email this weekend. And again, if some of you have taken the opportunity, but I do, like I said, I do teach Tuesday and Thursday, 1 o'clock, and at 4:15 Tuesday and Thursday, same class, but for GCC campus, same everything. In fact, you guys were ahead as far as the chapter that we're on than the rest of the class. They finally got done with chapter 8. Okay, so yeah, that's always open. So you just jump right in there, no problem. Okay, well, we ended up on any questions before I continue? Excuse me. All right, we ended up on chapter 8, specifically slide number 9, okay? But I'm gonna always take it back one page, one slide, just to kind of refresh your memory. This here dealt with the polyatomic ions, which is found on the periodic table, okay? The main thing to take away from these is that these are a group. Each one individually is a group. We don't change the name. We don't change the structure. If we need to add more than one of these groups, we put a parenthesis around the whole group, and then we use a subscript to designate how many of these groups we need, okay? Now, one thing also to remember is if we look, let's take a look at the one listed as nitrate and nitrite. And the name can be confusing sometimes, but let's break it down. Make sure there's no confusion. If we look at just nitrogen itself, when nitrogen itself becomes ionic, when it becomes an ion, remember that it is in group 5. Therefore, it will pick up 3 electrons, okay, and end up with a -3 charge, okay? When that occurs, we change the name to nitride. The suffix IDE, nitride. That happens to all the nonmetals that become ionic. So not only nitrogen, but phosphorus becomes phosphide. Okay, oxygen becomes oxide. Sulfur becomes sulfide. All the halogens in group 7, the fluorine, the bromine, and so forth. Halogens become halides, IDE, so chlorine becomes chloride. And so that tells you if you're dealing with the element or you're dealing with the ionic compound, okay? The ion of that nonmetal. So nitrogen becomes nitride. Notice that the moment nitrogen combines with an oxygen, as the case, next example down where you got 3 oxygens, that whole polyatomic group has a -1 charge, and that group is called nitrate, ATE, not to be confused with the IDE, nitride. When that oxygen has, instead of 3, there's 2, okay, because we got 2 different types of nitrogen-based oxygen groups. The next one is called nitrite, ITE. Okay, so the three names, nitride, nitrate, and nitrite, all involve oxygen. The 8 and the I, excuse me, let me restate that. All involve nitrogen, okay? Nitride, nitrate, nitrite. The 8 and the I have associated with it oxygens. And the number varies depending on the species. The same is true for sulfur. Sulfur, we know, itself. Sulfur all by itself, it's in group 6. And when it becomes ionic, it will pick up 2 electrons, okay? And we change the name to sulfide, okay? Now, when sulfur is associated with oxygens as a group, specifically 4 of them, it becomes a polyatomic ion, and it has a -2 charge, and that name is sulfate. Then if it has 3 oxygens, then that name becomes sulfite, okay? So we have the 8 and the 9, and there's more examples of this. In fact, I sent to you a couple of extra resources to, talk about the polyoxy ions, okay? Polyatomic ions. And I think we'll go through those two here after we're done with this chapter. All right. So polyatomic ions. A group, we don't change the name. We don't even change the structure. We need more than one. You put parentheses and use a subscript around the parentheses. All right, so the thing is about formulas for ionic compounds. When we put them together, at least for right now, they should be neutral, meaning that we put the total number of cations plus the total number of anions must equal 0. Okay, so sometimes it's a straightforward 1-to-1. I got 1 positive ion, 1 negative ion. I put them together to write the formula. But there are times it may be a ratio of 1-to-3, 1-to-2, or 2-to-3, or 3-to-2. It varies, but it must be put together such that all the positives cancel all the negatives to give you a 0. Okay, so for example, they ask you to combine sodium and nitrogen. And that's how they do it. Sometimes they'll tell you, here's the elements. Well, we can't combine the elements. We have to first convert those elements into ions, okay? And we know that sodium is in group 1. And when it becomes ionic, its oxidation number or its charge becomes a +1 because it lost that 1 valence electron. Nitrogen is in group 5. When it becomes ionic, takes up 3 electrons to fulfill that octet, and therefore now has a -3 charge, okay? Plus, like I mentioned, the name changes to nitride. Keep that in mind. And so we got to put together 1 sodium. We got a +1 here. Let me write this in here real quick. So what this tells you is that I need 3 sodium ions to cancel out the -3 of the nitride. So that 3 that I wrote in front of sodium ion now becomes the subscript, okay? So the formula is Na(3) nitrite. 3 positives, 3 negatives equals 0. All right, let's try this one. Well, we got the same scenario, okay? So if you're given the atoms, first step, and take a systematic approach at these. Once you become familiar with them, you don't have to go through this step. But what I do normally is I first take my atoms and convert it into ions. We just did sodium, we're familiar with that. So ionic sodium is a +1, okay? Sulfur, if you forget what its ionic charge is, find it on the periodic table. You'll find it to be in group 6. Group 6 tells you that I need 2 electrons to get to 8. So it will pick up 2 electrons. Sulfur also is a nonmetal. So you know that nonmetals gain electrons, metals lose electrons. So the overall charge for sulfur now is a -2. And guess what? Its name becomes, like we just talked about, sulfide. It went from sulfur to sulfide. You want to know that because we may need to name this compound that we put together. I got 1 positive for each sodium. That means I need 2 of them, 2 sodium ions for every sulfide ion, which then name-wise would be sodium sulfide. If I need to name them, but I put it down there because that way I'm ready for it in case I need to know the name. Okay, so there's a formula with the name sodium sulfide. The top one up here, the sodium nitride, its name was sodium nitride. The name changed from nitrogen to nitride when it became ionic nitrogen. Okay. Next one, we have magnesium and we have oxygen. Same step, systematic approach again, all right? So we break it down through the ions. We know that magnesium, we find it in the periodic tables in group 2. It will be a +2 because it has 2 valence electrons being in group 2. Oxygen, like sulfur, is in group 6. It also is a nonmetal. Therefore, it will pick up 2 electrons, giving us a -2 charge. And the name oxygen becomes oxide. Okay. And so we have magnesium oxide for the name. Okay. The charges are both equal. It's +2 plus -2. We could simply put them together as a 1-to-1. And there's our formula, MgO. Okay. Now, be ready to be prepared that eventually, to given the name, write the formula, given the formula, write the name, or given the elements, figure out the formula, then give the name. Just like we're doing right now. Next one. We have potassium and phosphorus. So we know potassium, again, is in group 1. And being in group 1, it will lose that 1 valence electron, okay, resulting in a +1 charge, okay? Phosphorus is in group 5, like nitrogen is. It will, being in group 5, it's a nonmetal. It will also, being in group 5, it will pick up 3 electrons. Okay, because it's a nonmetal, gains electrons, specifically gain 3 electrons because it's looking for that magical 8 number. Okay, and so we got it, we got the ion sitting there. So phosphorus becomes phosphide with the -3. Potassium, its name stays potassium. If we needed to designate the element versus the ion, we say potassium an atom or element, or potassium ion to designate which one we're talking about. So we got potassium ion with the +1. I need 3 of them to cancel out the -3 of the phosphide. And the name would be potassium phosphide. And its formula, that 3 in front of potassium, will be the subscript. Okay. So now we have K3P. Okay, this is a little more interesting, a little more challenging here, but let's break it down, systematic approach again. Break it down to the ions first. Calcium. Calcium's in group 2. Okay. When it becomes ionic, having 2 valence electrons, it will be a +2 charge. Okay. Nitrogen, we did that already. It's on top, group 5. It will pick up 3 electrons being a nonmetal. And so its charge is a -3. Okay. Now, the previous examples are pretty straightforward. You saw I got one had -3, and so I needed to add an X number of positives to cancel the -3. Here, it's a little bit different. We have a +3 and a -3. We can't simply put them together as a 1-to-1. Because if we did a 1-to-1, we still have a -1 net charge to deal with, which would be on the nitride, right? Because a +2 and a -3 results in a -1. And so we have to find a common number, just much like you would add two dissimilar fractions, 1/5 plus 1/7. We can't add those together, but we find a common number for 1/5 and 1/7, which could be 35. And then we convert each number to 35 to a common number, a lowest common denominator. Well, in the same manner, you can do this here. Can you think of a number that is common to both the calcium ion and the nitrite ion? What do you think would be a good number that is common to both? Anybody want to take a shot at it? Okay, we got. Okay, Catalina. That'll be great. Oh, Thomas, I just saw your question. You said you had a question about nitrite. Okay, we'll get to it. Let's go through this real quick. Okay. All right. So, Catalina, you said 2 calcium and 2 nitrites. That would be good. Why? Because if we put a 3 in front, if we need 3 calcium ions, that gives us a total of a +6, right? Charge. And if we take a 2, use 2 nitrites, that gives us a total of -6. Okay, so our common number here would be 6. And so those coefficients I just put there would be the subscripts for those particular ions. So it would be 3 calcium, calcium subscript 3, nitrogen subscript 2. Okay. We'll get to the formula here in a second. So we have calcium nitride would be the name. Okay. And so there we go with the formula. Okay. Yes, Thomas, I just saw you said you had a question about nitrate and nitrite.
Yeah, it's kind of a question about the nitrogen cycle. Like in aquaponics, the bacteria converts nitrate to nitrite, or maybe it's the other way around. Like, does the bacteria just eat that extra oxygen off of it, or it goes from nitrite to nitrate? Like, how could the bacteria convert one to the other?
That is a good question. I really don't know, to tell you the truth. My thought would be offhand that the bacteria must have an enzyme because a lot of the metabolism occurs using enzymes, and there must be an enzyme that is specific for that process in the nitrogen cycle to take the 8 and make it into the I, and vice versa too. And so then what it makes into a product, that oxygen could most likely candidate would be oxygen, but it could be used someplace else, maybe as carbon dioxide, or a variety of things. But I really don't know. That's a good question. You might check in the microbiology. Microbiology might look and see if there's any bacteria out there known to break down the nitrates and nitrites, and maybe they'll give you a cycle on how they do it.
Okay, thank you.
Yeah, no problem. All right, so with respect to dissimilar charges, when we put them together to write the formula, the point to take away from number 4 here, example number 4, is to find a common number. And then another little tidbit that can assist you is if you look at the formula we just created, okay, we had a subscript 2 for nitrite, right? All right. Well, think about this. Wasn't that the original charge for the calcium? Yeah. And if we look at the 3, the subscript 3, wasn't that the charge, the oxidation number for the nitrite was a -3? Yeah. And it's almost like you can cross the charges, the oxidation number, and they become the subscript. So I could at a glance, if I needed to know what is the charge, if I didn't know what calcium was with respect to its charge, I just look at the subscript of its partner. That tells me, okay? Look at, you can do that for some compounds, not all. Look at the number 3. Potassium has a -1. Well, the subscript for phosphorus, phosphide, is a 1. It's understood to be a 1, right? And then the subscript for potassium is a 3, which is the -3 charge for the phosphide, okay? Now, you can't do it for all those molecules. For some magnesium oxide, you can't do it because you don't know. It's a 1 there, and that doesn't make sense there, right? But we do know there's a +2 for magnesium and a -2 for oxide. All right. Oh, I cleared up all my examples. Okay, so here we have aluminum and chlorine, excuse me. Okay, so step number 1, we first write the ions. Aluminum is a metal. It's in group 3, has 3 valence electrons. It will have a +3 charge. Okay. Chlorine is in group 7. Group 7, everybody in group 7, when they become ionic, for nonmetals, will gain 1 electron because they have 7 valence electrons and they're seeking that magical 8, which means they just need 1 electron. So they will have a -1 charge because they picked up 1 electron. I think sometimes the confusion is, well, if I lose electrons, do I become positive or negative? Well, remember, the electrons are negative charge. As you lose them, you become more positive, okay? That might happen. And the converse of that is this, again, electrons being negative, as you pick up more negativity, you become negative, right? Okay, so that'll help you out to remember what's my ultimate charge. Then eventually you do it the old-fashioned way. You didn't do anything to the protons, you'll have a positive, and count the number of electrons you have left over, and you should have either equal number of protons and electrons to give you a net 0, which is the element, or if you lost electron, you end up with a net positive, and if you add electrons, you end up with a net negative. Okay, so here you can see that we need 3 chlorides. Notice the name. The name went from chlorine to chloride. That would be true for bromine. It goes to bromide. Iodine goes to iodide. Okay. Name, nothing happens to the metal. It's aluminum chloride. Okay. And our formula becomes AlCl3. Okay, zinc and iodine. Zinc, we know that. I talked about the charges. Now, let me rehash that because to refresh your memory. Okay, hold on. All right, so here's the periodic table. You know 100% of the time to charge the oxidation number for 16 of these elements when they become ionic. Group 1, everybody in group 1 with the exception of hydrogen, we're talking about metals only, will have a +1 charge. They have 1 valence electron. Everybody in group 2, which I've highlighted here in red, will end up with a +2 charge. So right there, you got 12 elements, okay? The other 4 are aluminum. it's in group 3, number 13. Always will have a +3 charge. Then catty corner, one way to look at it is maybe from aluminum. You can see how it goes at an angle to the left, and then we shoot across from silver to cadmium. So aluminum has a +3. Zinc always has a +2. Silver, Ag, always has a +1. And then we move back to the right. For Cd or cadmium, always has a +2. So here are 16 elements that when they become ionic, you know that their charge, their oxidation number 100% of the time. That means that all the other metals have a variable oxidation state. In fact, they can vary from a +1 to a +9, depending on the conditions. So we don't know what they are. We can't predict those, but we will know the anion, the partner charge 100% of the time. That will allow us to calculate what that metal is as far as its charge. And so what we mean by this, when we talk about the, let me find a different color here. When we talk about the anions, I'm going to talk about nitrogen and phosphorus, okay? Because that's mostly the one you see 100%, a lot more of. Nitrogen, phosphorus, both in group 5, excuse me. They're nonmetals, they will have a -3, okay? -3. Oxygen, sulfur, those are the main ones we generally talk about a lot more. We use the C a lot. It doesn't mean the other ones aren't there, but the oxygen and the sulfur, groups 6, always have a -2. And then the halides, fluorine all the way down here. Again, those are the ones I highlighted, the ones that you see more often, okay? The group 7, they gain 1 electron, always have a -1. And so those guys, when they're by themselves, I repeat, when they're by themselves, because you saw nitrogen hooked up with 3 oxygens, that's the nitrate. It's a totally different ballgame there. But when the elements are by themselves and they become ionic, those are the respective charges that they have. And so maybe I can say -3, -2, -1. Maybe that would work, okay? And so that means that a lot of times, and then plus all of the polyatomic ions over here, okay? They have a known charge. The charges are either a -1 or a -2 or even a -3, and only one cation there. But you know those charges, the anion charges 100% of the time, which means that all the other metals around here have a variable oxidation number. And we may not know what they are, but we can calculate them based on what they're partnered with. And remembering that the total number of cations plus the total number of anions must equal 0 for the compounds that we're using. A more general and better equation would be total number of cations plus the total number of anions must equal the overall charge of the molecule, which the majority of the time is a 0. But you can have charged particles and you can calculate. And we'll give some examples of that. You can calculate the oxidation number of them. All right, so let's go back to these. So zinc, okay, zinc has a +2 charge. It's one of the, now, why did I mention those 16s? Because that's important with respect to the name. Because notice here, the names I've been putting so far, I said sodium sulfide, magnesium oxide, potassium phosphide, calcium nitride, aluminum chloride. Now I'm going to call this zinc with a +2 charge. And then the I then becomes iodide with a -1. Okay, that means I need 2 of them. To cancel the -2 of the zinc. So the name itself is zinc iodide. Okay, that's what you ingest in your salt when you are ingesting iodized salt. It is a sodium iodide, maybe a potassium iodide. You know, I'm not familiar of them using iodine in your salt. Okay, all right. So we got the name here, the formula Zn I subscript 2. Now, and the name zinc chloride. When it comes to naming the metals, the 16 are, like I said, are constant oxidation numbers. We don't have to decipher them. We're going to learn here. Let's say we're dealing with copper. Well, guess what? Copper is not part of the 16. There are 2 types of copper. There's a copper +1 and a copper +2. And the question is, well, how do we distinguish between the 2 when we want to talk about it? And that's when we use Roman numeral to distinguish copper 1, which is Roman numeral 1, and copper 2, which is Roman numeral number 2. Okay. The other 16, because they have a constant oxidation number with respect to the metals, there's no Roman numerals to distinguish them. It is simply sodium sulfide. That's sodium Roman numeral 1 sulfide. All right. And this is what this means here. Copper Roman numeral 2. They have to tell you which copper you're working with. Okay, and that's true for all the other metals that are not part of the 16. Or if they don't tell you, you're going to know what the partner is. So you can calculate what that oxidation state is. But here they're telling you, and that Roman numeral belongs to copper, has nothing to do with anything else, okay? It has nothing to do with being in group 2 on the periodic table, because that's group 2A. This is strictly Roman numeral 2, period. No A, B, no nothing else. It just says that copper, in this case, has a +2 charge, okay? And oxygen, well, we know it's in group 6, like we did for number 2 up here, and for magnesium, it's going to be a -2 ion, okay? Because it picked up 2 electrons, and its name changes to oxide. Okay, so here, we can simply put them as a 1-to-1 because we got a +2 and a -2. As the case with magnesium and oxide, they cancel each other out. So structurally, it's simply a CuO. But the name, we do copper, and then we keep the Roman numeral, and we know that oxygen became oxide. Okay. And there's the formula. There's the name, copper 2 oxide. Okay. Now here's the next one, Pb, which is lead. They're telling you Roman numeral 4, which states, okay, you must be dealing with copper +4. And that is correct. Oxide again, or oxygen again, has a -2 charge, okay? Group 6 picks up 2 electrons, non-metal. All right, so we need to balance that charge of +4. So that tells us that we need two oxides to cancel the +4. So that 2 becomes a subscript. The name, LEAD, Roman numeral IV, which is 4 oxide. Okay. And the formula is PbO2. Now, it gave you the names here because sometimes you are given the name and being asked to write the formula. And so you can see the name lead 4 tells you you're dealing with lead plus 4. And oxide tells you you're dealing with the oxygen, obviously, with a -2. And you have to put them together such that the charges cancel out. So you end up with PbO2. Okay. That's it. Sometimes they may give you the elements and ask you to write the formulas, or sometimes they may give you the name and ask you to write the formulas. All right, so let me clear this out. You must, check the charges, make sure everything adds up to 0. But like I was stating, a more accurate equation, I think, would be if you say that the number of cations, remember those are the ones with the plus charges, plus the number of anions, those are the ones with that negative charges, equal the charge the molecule / compound. Okay. And if you use this general formula, it will encompass a lot of situations. In fact, in your homework, you may find that you're dealing with compounds that have a charge. Okay, well, okay, how's that? How can we use this? Well, let's do a quick example. I can give you a hypothetical. Well, I'll do an exact one for sure. Sure. Let's take now metalloids rarely. I shouldn't say rarely, but really, we're not gonna work a lot with metalloids with respect to compounds. Here, you may be asked, how many electrons they can gain or lose, or how many valence electrons, but there's a whole area in metalloids that it's extremely fascinating, but unfortunately, because of the properties they have, properties of metal, properties of non-metals, it's fascinating. But that's for another, and that's for an upper level class. Okay, so let's take a look at, let's say, let's do this. Let's do nitrate. We had talked about nitrate, one of the polyatomic ions, right? And it's subscript, and then we know that has a -1. Okay. The question is, what is the oxidation number of nitrogen as a nitrate? Okay. Now you may think, well, I just go to the periodic table and look that up, and you'll be incorrect, because the nitrogen, the oxidation state of nitrogen by itself, yes, would be a -3. Okay. But nitrogen here is bonded to other oxygens. So something else is happening here. Okay. Now, we use a general formula. And so 99% of the time, the first entity that is written, the first element that is written, okay. Now, when it comes, well, let me restate this. When it comes to ionic compounds, okay, when it comes to ionic compounds, the metal 9 times out of 10 is written first. Then the non-metal follows when we read out the formula. Okay. Now, for covalent compounds, which this is, the nitrate, even though it's got a charge in it, it is a covalent compound. It's made up of nothing but nitrogen and oxygen. 9 times out of 10, the first element is the central atom. We talked about that, the central atom, and everything else is bonded around it. So nitrogen is the central atom, okay? And we got oxygen bonded around it. Now, we don't know what its oxidation state is here, but we can calculate it because we know the oxidation state of the partners, which is the oxygen. So we use that general formula, number of cations, and it's a general formula. I should say the number of positive, I just call them cat. positive charged entities and cations, because we can think of the nitrogen as a cation here, but not really a true, it's gonna have a positive charge, okay? So we can say nitrogen plus, we have 3 oxygens, and each one has a -2 charge, okay? And that means that we have a total of -6 for the oxygens. And then the whole species, because it's a polyatomic ion, has a charge of -1. And that's what I meant. Normally, a lot of times, the compounds we play with and put together have a 0 charge. But occasionally, especially if you're dealing with polyatomic ions, they have an overall charge. And in this case, it's got a -1 charge. Now, what does that mean? Well, what we do, we got an algebraic equation here. We solve for N. So N, which is nitrogen, is equal to -1. Oh, what did I do? -1 plus a 6, right? Because we have -1, we add +6 to both sides of the equation. That cancels the -6 on the left-hand side. And so now that is equal to 5. So in this state, the nitrate in the nitrate condition of ion, nitrate polyatomic ion, nitrogen has an oxidation state of a +5, okay? And you can use this equation, the general equation, for multiple things. I know when your homework comes up, you're going to see some crazy looking compounds and hypothetical compounds, but no worries. Use that general equation, you can solve for it. And occasionally you can end up with a quarter charge or half a charge, because what's happening, this charge is being shared amongst 2 elements. Okay, in fact, you might have like 2 phosphorus and 5 oxygen, and that charge is shared amongst those 2 phosphorus. Anyway, so the charges here, they're telling you it may equal to 0 or the overall charge of the molecule. So polyatomic ions. We briefly mentioned about those earlier, about the table, okay? If we need more of these, we're going to use parentheses. So if we look at here, we look at magnesium, we look at hydroxide, OH, okay? That is a polyatomic ion. We're also given the charge of the polyatomic ion, which is a -1. So you need to convert the magnesium to an ion. We know that magnesium is a +2. It's in group 2, so it will have a +2 charge. The hydroxide has a -1. We need 2 of them. So what that means is we need a parentheses with the subscript 2, which tells us we have 2 hydroxide. The name here becomes, this is important because I see so many different naming situations, and you don't have to do that, okay? This is a polyatomic ion. That OH minus has a name. It's on the table. It's called hydroxide. We don't change that. It's just simply hydroxide. It's not hydrogen oxide. It's not that at all. It's not dihydrogen oxide. It's not anything of the sort, any combination. It is simply hydroxide, okay? And I direct you to the periodic table again. Right there, okay? They all have their own specific name, the polyatomic ion, and that is what you use to name them. Okay, so that's magnesium hydroxide. All right, well, here we go. PO4 -2. That looks very complicated, but recognize, you might think phosphorus, Okay, you might think phosphide. However, right immediately after phosphorus, you see an oxygen. So that tells you, no, it's not phosphide. It's got to be an 8 of some sort because it's got oxygen. Well, you go to the periodic table, look for it. You got down here, PO4 with a -3. Its name is phosphate, okay? Phosphate. And so we got potassium that we know is in group 1, and it has a +1 charge, okay? And so we can do this. We know that potassium has a +1 charge, which tells you that I need 3 of them, okay? Because there's a -3 on the phosphate. So I got the formula there, okay? And so let me write the names here as we go along. I lost that magnesium. Magnesium hydroxide. Potassium phosphate. Okay. And another polyatomic ion called sulfate, SO4 -2. And silver is part of the 16. You can see that list there, that's a +1 charge. And that means that we need 2 of them, okay? Because each one's a +1 charge. Someone had a question. Okay, good question. The question number 2, it says PO4, why doesn't it need parentheses? You only need the parentheses if you need more than one, okay? More than one, you put a parenthesis. If you only need one, in this case, you only needed one PO4, one phosphate, you just leave it like that. All right. And so here, again, same scenario, SO2, but we're going to need 2 silvers. All right. And so the formula becomes silver 2. I'll type it out, name-wise, silver sulfate, not to be confused with the sulfite, ITE, which is 1 less oxygen, okay? Totally different species. Okay, and again, you notice that there's only 1 sulfate. We only need a 1 sulfate entity, polyatomic ion, so we don't need a parentheses also here in this case. All right, let's do the next one. There we go, calcium nitrate. Okay, well, what do we know about calcium? Calcium has a +2. It is in group 2. So the calcium ion is in +2. So now we can see that the nitrate is a -1. So that indicates that I'm going to need a parenthesis here because I'm going to need 2 of these guys because each one has a -2. So that 2 becomes the subscript. Okay, so calcium nitrate is the name here. Not to be confused with nitrite, which is 1 less oxygen, NO2. All right. We're told which ion we're dealing with, the copper. Okay, Roman numeral 2 tells us we are dealing with a +2 copper. CO3 is another polyatomic ion. We find it in the periodic table. That is the carbonate. We're using copper 2, and so the formula is a straightforward CuCO3. Again, the CO3 you only need 1, so no parentheses is necessary. naming, we have to use the Roman numerals here. Copper, Roman numeral 2, carbonate. And you'll find that polyatomic ion again in the table, periodic table. Okay, so the point here, use the parentheses when you need to use more than one of the polyatomic ions. And if you only need one polyatomic ion, you don't need the parentheses, okay? Just leave it as so. All right, any questions about this part? All right, here we're talking about naming ionic compounds. I have been introducing that as we progress, okay? And the naming depends on the fixed or the variable charge. If we have a fixed charge, I'm sure I hope you see the trend here like so far. Of the 16, we don't use Roman numerals. It's straightforward, whatever metal that is. It is only when it's a different, a variable charge metal that we use Roman numerals to name them, okay? So the metal name, fixed charge is a straightforward. We get the metal name plus the non-metal that we now add the suffix IDE. So NaCl becomes chloride. We talked at length about this, okay? All the non-metals, when they're by themselves, have changed the N to IDE, okay? If they're hooked up with oxygens, then we are dealing with eights and ites. Most of them is eights and ites. There's some other ones that we're going to talk about. The majority of them are an 8 or an ite. So we got sodium chloride here. For example, we got K and Br. Okay. K, simply potassium. Br is bromine. However, because it's bonded to potassium, notice the metal is written first, followed by the non-metal. Then this bromine is bromide. So this is potassium bromide. Okay. Oh yeah, I was going to say something back here. Notice here, you can start. We went the first example, magnesium hydroxide, but you can combine that with the phosphate or the sulfate, magnesium nitrate, magnesium carbonate, potassium hydroxide, potassium sulfate, potassium nitrate, potassium carbonate, silver hydroxide, silver phosphate. Do you get the gist of it? Okay, so you can do a lot of mix and match here. Mix and match all the different anions and cations. I mean, this just the 5 here. There's 25 different combinations that you can do with just this page. And as you notice as we go along, we're adding others that you can right here. We combine sodium sulfide, but you can combine sodium oxide, sodium phosphide, sodium nitride, sodium chloride, sodium iodide, sodium oxide, etc. And so here you got another, I don't know, 64. So, you're probably at about 1,000, what we talked about so far, maybe 1,000 or more combinations of compounds that we put together. Eventually, even when we get into study mate, I'm going to mention that's roughly about 20,000 combinations of compounds that you can put together. That's just ionic compounds and just mixing and matching the cation and the anion. So, in fact, you might start reading the labels of stuff you eat. Be surprised that you become familiar with. Oh my God, I'm eating this. All right, magnesium hydroxide, you find a lot of that in milk of magnesia, by the way, speaking of eating stuff. It's a base and reacts with the acid in your stomach to kind of reduce the acid content, which, by the way, is one of the 6 types 6 different types of chemical reactions, neutralization, magnesium hydroxide. All right. We got the name here, phosphate. We need 3. We got this already. Hold on, what am I doing? I jumped forward. There we go. So potassium bromide. Okay. We got magnesium and we got oxygen. Oxygen becomes oxide. Okay. And so this becomes magnesium oxide. The metal part never does not change its name. It is what it is. It is the non-metal part that has a name change. You might think here, okay, I got F2. You might want to think diatomic fluorine, but don't think that way. Why? Because right before the F2, you have a metal, calcium, and then followed by the halogen here, the fluorine. So that is an indication of an ionic compound. If the calcium was not there, then yes, you can say, I got fluorine, the elemental fluorine. But you got calcium written first, followed by the fluorine, tells you I got calcium fluoride. Notice something here. We have not been using any prefixes. We changed the suffix of the non-metal. But for example, we didn't say calcium difluoride, okay? All right, or nor did we say magnesium monoxide or anything like that. And that is something to remember here. When it comes to ionic compounds, there are no prefixes like a mono, di, tri, etc. Okay, there will be with covalent compounds, but not with ionic compounds. Okay, so in this case, we got lithium, sulfur become sulfide. Okay, and so its name is simply lithium sulfide, not dilithium sulfide. Okay, which I don't know if you're a Star Trek fan. I often wonder why dilithium crystals, what they were. Okay, they use that in the program. So I don't know. I don't know, maybe it's 2 lithium atoms for all I know. Anyway, lithium sulfide. Then we got Ag, which is silver, Cl, which is chloride. Simply put, silver chloride. Okay. All right, no prefixes involved with ionic compounds. You can mix and match here. Here we did potassium bromide, but you can go potassium oxide, potassium fluoride, potassium sulfide, potassium chloride, and the same with the others. So you have even an additional 25, 30 combinations here to your data, to add to your database. All right. Polyatomic ions, we talked about that, okay? Now, you might think, well, how do I know if I have a polyatomic ion? Well, let's take a systematic approach to it. So I got here K3PO4. And I see this and I see, okay, I got potassium. All right, that's given, that's a metal, followed by a non-metal, which is phosphorus, okay? Now, you might be tempted because it's phosphorus, say, maybe I'm dealing with phosphide. However, look immediately to the right of phosphorus, and 99% of the time, you're going to find an oxygen sitting there. When that occurs, then don't think phosphide single, think polyatomic ion. That sends you to the table, look for PO4, okay, which you'll find has a -3 charge, which is consistent with the formula of 3 potassium. And you'll find that you have the name phosphate, okay? Not phosphide, because phosphide would be K3P, okay? P by itself. Note the difference, okay? Because the formula had immediately following the phosphorus, you had an oxygen. Okay, in this case, you see a formula and then you see a parentheses. Automatically, you see a parentheses, think automatic polyatomic ion. Okay, so then you see inside the parentheses OH, send you to the table. You'll find that OH is the hydroxide. And so you have calcium hydroxide. Calcium hydroxide. if you eat a lot of Tums, this is what you eat, calcium hydroxide. You might read the label where it says this is good for bone structure and so forth. That's because the calcium involved there. The hydroxide is the base that reacts with the acid in your stomach. Okay, now, same scenario with the phosphorus. And we did the first case, we see sulfur, we see zinc, followed by sulfur. We might want to think sulfide, but then right immediately next to the sulfur is oxygen. Okay, there's 4 of them, exactly 4 of them. So therefore, that sends you to the polyatomic table, and you find it to be sulfate. So the name here would be zinc sulfate. Okay. And I think maybe if I write this, if it were zinc and simply sulfur, then that would be zinc sulfide. Okay. If it were potassium, K3, and phosphorus, that would be potassium phosphide. Note how the IDE is an indication of just the element by itself. Okay, the 8 tells you we're dealing with the element, whatever this first part of the 8 is. That element, we're dealing with oxygen, either 3 or 2 or 4 and 3, depending on which polyatomic ion you're working with. Okay, let's clear this up. Now we introduced the variable charge metal ionic compounds where we have to give it the name, and then we use a Roman numeral in parentheses to tell us what is the oxidation state of that metal. And then the non-metal, as always, we do the IDE. We add the IDE to it. And so here we have copper. All right, well, you might think, well, wait a minute. How do I know which copper? You know, you find it and you say, okay, I got copper, it's not part of the 16. Okay. Not copper, not part of the 16. So which one do I use? Okay. Well, like I said, you always are going to know the charge of the partner. And remember, number of cations plus number of anions equals the charge of the molecule, the compound, which in this case is 0. So what do we know about the chlorides? The chlorides each have a -1, right? And so that means that we got a -2 sitting there for the chlorides. And so copper minus a -2 equals 0. So that means that I must be using a +2 copper here. And if that's the case, then it's copper, Roman numeral 2, chloride. Okay. By knowing what the charge is on my partner, which is the chlorides. And so that's the name, copper 2 chloride. Okay, same scenario here, similar. Okay. Lead, we don't know what it is because it's not part of the 16, so it's got a variable charge, but we know what the oxide is. We know each oxide is a -2. And so I can write a general formula where PB minus -4, right? Because each one is a -2. I got 2 of them, and that is equal to 0, which tells me that the lead is equal to a +4, which tells me that I'm working with lead, parentheses, IV, and parentheses, oxide. Okay. There it is. All right, here's nickel. Nickel and bromide. We know, like the chloride, that they have a -1. And so with that being the case, where am I at? Hold on. Okay. Knowing that nickel is a -1, then I know that nickel, okay, plus I can do it this way, a -3 because I got 3 bromides, that's equal to 0. Okay, which is simply, the same thing as nickel -3 equals 0. It's the same thing, which tells me that I'm working with nickel plus 3. Okay, because I'm solving for that. So nickel is a +3, which is Roman numeral 3. Nickel, Roman numeral 3, bromide. Okay, again, no prefixes here for the 3 bromides, just strictly bromide. Okay, manganese. Well, all right, so I'm looking at this and I see, all right, I see sulfur. My first indication is sulfide, but then I noticed that I got an oxygen immediately following that. So now I'm talking polyatomic ion. And I got 4 oxygens. So definitely polyatomic ion attached to the sulfur. Okay. I go to the periodic table. That gives me, in the polyatomic ion table, it's a -2 charge. -2. That means that the manganese here must be a +2. Okay. Because of the sulfate is a -2. So I got manganese, Roman numeral 2 sulfate. Okay, here we go with copper, excuse me. A similar scenario. I see my nitrogen, I'm thinking nitride, but then I see oxygen immediately right next to my nitrogen. And specifically, I got 3 of them, 3 oxygens, so it's polyatomic ions. Go to the table, that's nitrate. I notice that each one has a -1, okay? That suggests that copper has to be a +1. Okay, so I'm using copper 1 nitrate, not nitrogen trioxide, but nitrate. It has its own specific name. Okay. So, and let's see, do we have one more? Okay. Now, I got cobalt, CO, okay? Not to be mistaken with C uppercase O. CO does not equal C little o, okay? C capital O is carbon monoxide. C little o is cobalt. All right, so I got cobalt, and lo and behold, hey, look at this. I got nitrogen. I look to my right. Hey, no oxygens attached. Okay, it's nitrogen all by itself. That tells me it is nitride. Okay. And furthermore, nitride has a -3 charge, which tells me that this must be a +3, the cobalt. Cobalt 3 nitride. Okay, nitride. Again, note the difference between H and I. Nitrite versus nitride. And then even at that, if you had, let's say, copper NO2, that would be copper 1 nitrite. Nitrite, because I got 2. Okay. All right, now a little bit more of a challenge, but it shouldn't be, okay? We can break it down here. All right, so we look at this and we see parentheses. Boom, parentheses. Polyatomic ion. Okay. So we go to the table because now we got CO3. And we looked that up, and that's the carbonate ion. Okay. And the carbonate ion, based on the periodic on the polyatomic ion table, has a -2. All right. So we can do it a couple of ways. I'm going to set it up as an algebraic equation. So I have two irons, right? Because I got Fe2. So I got two Fe. Remember, so that is the charge total number of cations. Now, the total number of anions, we just looked that up. You put it in the table and you see that CO3 is the carbonate and that each one is a -2. Now, based on the parentheses, the subscript, there's 3 of them. Okay, so 3 times -2, isn't that -6? And the overall charge is 0. So you have a very simple algebraic equation here. We're going to solve for iron. And so rearrange the equation. I'm going to add +6 to both sides of the equation. So I got F2Fe is equal to +6, right? And then I divide through by 2 to get rid of that 2 over there by the iron. And so I end up with Fe is equal to 6 divided by 2, and that is equal to +3. And so the iron that is being utilized here has a +3 charge. Okay, and so therefore I'm using iron Roman numeral 3. And in this case, would be called carbonate. But I needed to figure out first which iron I'm using. Okay. And that's how I did, because that's what I did here. I set it up as an algebraic equation because I know total cations plus the total anions in this case equals 0. Okay, there's no charge in the whole molecule. And so I know that the carbonate, CO3, has a -2 each one. Why? Because I go to the polyatomic table and I see that CO3, the carbonate, has a -3 too. The parentheses tells me I'm using 3 carbonates. So I have a total of a -6. So I set up my equation, 2Fe plus -6 equals 0. I solve for iron. That tells me that each iron has a each iron has a +3. And it makes sense. Plug in the +3 back into the first equation of iron. So +3 times 2 is 6 minus 6 equals 0. There it is. Okay. And so I'm working with iron 3 carbonate. Now, very quickly, you know, because I said earlier that when you look at the cation, well, let me do it this way. If I look at the 3 here for the number of anions, that turns out to be the oxidation state of the cation. And isn't the subscript for the cation? That is the oxidation state for the anion, the -2. So I could, at a glance, just looked at the subscript for the partner, the anion, and tell me right away what the charge is on the iron, which in this case is the +3. But if you don't see it, work it through, set it up as an algebraic equation, and just like we did here in blue, to figure out which iron you are using. Okay. All right, I tell you what, why don't we take a quick break here? It's 2:15. What do you say we come back at 2:25? Okay, I will stop sharing for a minute. Okay, I'm back. So here on this slide, they're asking you to give either the formula or give the name. Okay, so break it down. So number one, we have SR. Well, we got to look that up, right? If you're not familiar with that, SR is a metal. It's in group 2 strontium. It's underneath, right underneath calcium. Okay. Being in group 2 and being a metal, when it becomes ionic, it will have a +2 charge, right? Just like calcium and just like magnesium. The OH minus is a polyatomic ion. And so I'm going to need 2 of those. Okay. And so I'm going to put my handwritten one first, and then we'll do the one that's a little bit neater. So SR parentheses OH2 subscript Q, strontium hydroxide. Okay. We don't give the Roman numeral 2. Why? Because it's part of the constant oxidation number, the fixed oxidation number, not a variable. So it's just strictly strontium hydroxide. All right, so now we go to number 2. We have AU, which is gold. Okay, but the question is, all right, which one? Because gold is not part of 16, so we're going to have to use Roman numerals here. Question is, which one? All right, well, what do we know about the partner here? We know that the chlorides each have a -1, and we got 3 of them. That implies that gold must be +3, okay, because we have 3 chlorides here, each with -1. And so therefore we have gold, Roman numeral 3, chloride. Okay, the zinc, number 2, zinc is part of the 16, always has a +2. Oxygen, group 6, it's the oxide. And so basically here, we're going to put them together as zinc oxide. All right. Excuse me. All right, so now we got the next one, number 4. We got barium. Well, we got to find it. What is this charge? We find barium is in group Q. That means ionic barium would have a +2 charge. Okay. The PO4, another polyatomic ion, okay, with a -3 charge. So we got a +2 and a -3. We got to find a common number. And that common number will be 6 again. So we're going to need 2 of the phosphates and 3 of the bariums. So we're going to need a parentheses for the phosphate because we're using more than 1. And so we end up with barium 3, parentheses, PO4 2. Okay. All right. Next one, number 5, lithium, group 1. So it will have a +1 charge. Then the SO3, -2. We may be tempted to say sulfate, but double check that on the table. We'll see that we're dealing with 3 oxygens and not 4. Therefore, it is sulfite. Okay, so we're going to need 2 lithiums for the -2 to cancel those. So we're going to need a LiQ-SO3, lithium sulfite. All right, aluminum, part of the 16, we know it always has a +3 charge, is in group 3. Sulfide will have a -2, it's in group 6, okay? Now we have a dissimilar charge here. We got a +3 and a -2 to put together, very analogous to number 4. Okay, just the other way around. So we're going to need a common number of 2. So we're going to need 2 aluminums and 3 sulfides. And so our formula would be Al2S3, aluminum sulfide. And here we're asked to just name the species. Well, we got a parentheses here. Okay, that tells you polyatomic ion. We go inside, we're dealing with nitrogen bonded to 3 oxygens. That will be nitrate. Each one has a -1 charge, and we have 2 of them. Therefore, that infers that we're dealing with copper 2. And so we got copper, Roman numeral 2, nitrate. Okay. Pretty messy up there. Here, let me clear it up and give you the non-messy part. There you go. But it kind of gives you an idea how we kind of work through the problem, work it through so we could figure out what we need to write down. So there we go, strontium hydroxide, gold 3, chloride, zinc oxide, barium phosphate, lithium sulfite, aluminum sulfide, okay, and a copper 2 nitrate. Any questions so far? All right, here we got sodium nitrate. So we're given the name. We want to give the formula. Well, we'll break it down into the ions. And what do we know about sodium? Yeah, sodium is a +1. Okay. Notice here they talk about nitrite, not nitrate. So that is 2 oxygens, and each one has a -1. And so we got a +1 from the sodium, -1 from the nitrate. We can simply put them together as a 1-to-1. Okay. Nickel 3. All right. So we got nickel 3 here. So we got Ni +3. We know the oxides is a -2. And so we got to find a common number here again, which is 3. So we need 3 oxides and 2 nickel 3s. Okay, which would give us Ni2O3. Magnesium. Magnesium has a +2 charge because it's in group 2 now. It's an ion, it's a +2 charge. Iodide, keyword iodide. So it's just I. Each one is a -1 because it's a group 7. So we're going to need 2 of them to cancel the -2 of the magnesium. And so formula becomes Mgi subscript Q. Okay, aluminum, part of the 16, so it's going to have a +3 charge. The one that's cyanide, that could be a problem. The fact that it's cyanide is unusual. Go to the polyatomic ion table. And when you do that, you'll find this here. And so this means that each one has a -3. It's a copper and a nitrogen with a -3 charge. Remember, we did the Lewis dot structure in this guy. So I'm going to need 3 of these. And so I have aluminum parentheses CN3. Okay. All right, let me clear up my mess and give you the non-messy version. All right, there you go. Sodium nitrate, nickel 2 nickels, 3 oxides. Okay, so it's Ni2O3. Then we got magnesium, Mgi2, and then cyanide is the polyatomic ion, Cn, and we need 3 of them to counter the +3 of aluminum. Okay, now again, as we go along, as we're making these formulas, keep in mind that you can mix and match sodium with the oxide, sodium with the iodide, sodium with the cyanide, and nickel with the nitrate, nickel with the iodide, et cetera, et cetera. And so you see, you're building up your database of the compounds you're putting together. All right, which brings us to molecular compounds slash covalent compounds. These are compounds that are made up of nonmetals only. Okay, so no metals involved here. Now remember, the main difference between ionic compounds and covalent compounds is this. Ionic compounds, when placed in water, will dissociate. Now, some dissociate 100%, which we're going to learn about here. We're dealing with solubility rules, but some maybe dissociate maybe 5%. Nevertheless, regardless of the amount that they dissociate, okay, into their completely charged particles or ions. And that property allows it to conduct electricity. So if you were to take distilled water, that's 100% water, nothing else in there, and you try to run a current through it, a small current, it won't pass, no current will go through it until you add a little bit of ionic compound, which then dissociates, which then carries the current, and now you can get electrocuted if you jump into that water. If you literally don't do this at home, don't say Dr. Fred told you to do this, but okay, you can fill up your bathtub with 100% distilled water. Clean your bathtub up, okay? And plug in your hair dryer, throw it in the water, nothing's gonna happen because there's no ions. Now, the moment you jump in there, you're gonna be okay. Don't do this at home, I repeat. But we have salts and stuff in our body, and those dissolve into the water. So you probably be a few minutes before you will start feeling a little zing because of the ions in your body and the conduct electricity. But okay, molecular compounds do not do that, except for one type of compound, which are acids, and we're going to talk about that next chapter. But for right now, molecular compounds, when put in water, do not dissociate. Remember, they share electrons. They share that bond. Okay. Ionic compounds have an electrostatic attraction, like two magnets coming together. Covalent compounds don't have that. They share a bond. All right. So they don't have ions, so they don't have charges. So we use the term oxidation number because the oxygen, be it on ionic compound or a covalent compound, still has a -2 charge. Okay. But we don't say charge, we say oxidation number because the oxidation number encompasses both covalent compounds and ionic compounds. So I will be using the term oxidation number, keeping in mind that we're still talking about the relative charge. Added a small amount of Dr. Teal's. I'm not familiar with Dr. Teal's. Oh, bath salt. Okay. Yeah, well, Dr. Teal's are, obviously salts. I'm not sure what exactly all those salts are, but my guess, you probably got some magnesium salts in there and some calcium salts, which are soluble. So yes, once you had distilled water 100%, you dumped in any type of salt, and then you have something that can conduct electricity. Yeah, and especially if you throw an electrifiance in there, it would definitely hurt somebody. Okay. All right. So Yeah, but don't, forensic science. I mean, some of the questions I get is like, well, we won't go there, but I'm not telling you to do this at home. I'm not telling you that this is what you can do. No, I'm not telling, I'm just talking chemistry here, okay? Try to give you a real life examples that are familiar. And because sometimes we see them in real life and we don't put the two, that's chemistry, Anyway, so whenever I get a chance, I try to bring in real life examples. All right, so as we talked about with ionic compounds and naming, other than using the Roman numeral for the ones that had a variable charge, we don't use any prefixes. But over here, we do with respect to covalent compounds. We use the prefixes mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa 6, hepta 7, octa 8, and occasionally you see 9, nana, NO-NA, and 10 octa, OCTA. Okay, that gives you a number because we really now have to talk about how many of atoms, non-metal atoms we're dealing with. Okay, so how do we do that? Well, first part in green, if it needs a prefix, you put a prefix plus the non-metal name, okay? And then we follow that by the prefix if necessary, and then follow that by the second non-metal name, and we add the IDE. The IDE comes along just like we did in ionic compounds. So oxygen becomes oxide, be it in covalent compounds or be it in ionic compounds, okay? Sulfur, depending if it's bonded to it or if it's standalone, will be either sulfur or sulfide, depending how it's bonded. And you're always going to know whether it's a central atom because, again, 9 times out of 10, the first element that you see written is a central atom. The only exception to the rule is water. I mentioned this, H2O. Just by convention, that's how they write it, H2O. Oxygen there is the central atom. Technically, it should be written OH2, because oxygen is the central atom, but it continues with H2O. All right. If the first non-metal is by itself, we don't use the prefix mono, okay? Only if there's more than one. So, for example, we're all familiar with this one, CO2. First non-metal is C for carbon. Second one is oxygen for oxide, and there's 2 of them. So carbon is 1 carbon, so there's not monocarbon, just simply carbon, and it's carbon dioxide, okay? To tell you that there are 2 oxygens on that carbon, okay? So count with respect to CO, again, same process. We got carbon is the first non-metal, okay? Followed by oxygen, which is now oxide. And there's only 1 of them, so we have to designate it as to how many, so it becomes carbon monoxide, okay? And we're familiar with this one, carbon monoxide, poisonous gas, one of the gases that are emitted in our vehicles, and so is carbon dioxide. Okay, now let's take this. Now we got the formula. My suggestion, again, systematic approach, is to first write I want to call it the parent name, probably the base name, and we're dealing with phosphorus and oxygen, which is now oxide. So phosphorus is the first one, so it stays the name phosphorus. It's not phosphide because it's the first name that is a central atom. In fact, there's 2 of them here. Okay, so it stays phosphorus. And then followed by oxygen, which again, like we said, now changes to oxide like the ionic compound. So that is the parent name, the base name. I don't want to call it the parent, the base name. Now we go back and add prefixes. We see that there are 2 phosphorus. So we say di. If it was just one, we would just leave it phosphorus like we did with carbon, okay? Then we go to the oxide, and there are 5, and penta is the prefix. Now, here's the English. The English people have told me, tell me this, that when you have 2 vowels and you're going to put them together, like we're doing here, you got the A and the O, that the A needs to be dropped. Okay, and so technically, from an English perspective, it's you drop the A and then you put in the pen, so it's pentoxide. Okay, if you forget to drop the A, I'm not going to make a big deal out of it. It's fine. Pentoxide, pentaoxide, same. To me, it's the same stuff. Okay. All right, so that's the name. Notice in this example, they forgot to drop the A. Okay, so parent name, base name, then go back and put the prefixes. Here we got this one. Here, in this case, we got 1 phosphorus, so we don't have to use mono. Remember, 1 phosphorus, you leave it alone. And then we got the fluorine, which is bonded to the phosphorus, but we changed the name like we did with the ionic compounds, is still fluoride. All right, and there's 3 of them. And so that's phosphorus, fluoride. And so you can systematically do what we just did with the first one, is put down the base name, and then the name of the other nonmetal, which is fluoride. That is the base name, and then come back and add the prefixes. Okay, trifluoride. There we go. Oh, excuse me. Okay, here we have iodine. Iodine is the first nonmetal put down, so it's the central element. And then attached to that are more fluoride, like the previous example. Oh, gotta learn how to spell F-U-O. Fluoride. I had a senior moment there. Okay, so that is the base name again. We got 1 iodine, we leave iodine alone, okay? And then we have 7 fluorides. 7, the prefix for that is Hep. Okay, here we don't have to drop the A because we have don't have another vowel in there. The F is not a vowel, so it's heptafluoride. Okay. All right. So as the case we did before, you could be given the name, or you can be given the formula, or vice versa. But either way, be able to go in both directions here. Okay. And so that's why I had the double arrow. All right, given the name, given the formula, write the name and vice versa. So here we have this one. All right, so we got BR308. All right, so systematic approach. Okay. Break it down to the parent name. Br is bromine. It is the first non-metal element presented, so therefore it is a central atom. There happens to be 3 of them. There's a big old complex here, complicated compound that is put together, but there's 3 of them, okay? And, excuse me, so it name stays a bromine. And then the oxygens, as always, are oxide. So that is the base name, okay? We have 3 of them, 3 bromines, so that's tri. We add the tri. And we have 8 oxide. So octa, okay? Drop the A, octoxide. Octoxide, it's a little bit of a tongue twister. Okay, if you left the A, that's fine. All right, here we have phosphorus and sulfur. Now remember, I said sulfur could be up front first and it stays the word sulfur, but sulfur here follows another element. So that becomes sulfide. See, notice the difference? You'll see here in a second another example. So we had the base name and sulfide. Sulfide, because those sulfurs are bonded to the central atom, which is the first element. Okay, so that's the base name. Now you go back and add the prefixes and you end up with tetraphosphorus heptasulfide. Okay. Now here's the difference here. Notice something. The sulfur is first. Unlike the previous example, the sulfur was second and the name changed to sulfide. But here, the sulfur is first. That tells you that that is the central atom. Okay, so that name stays sulfur. And then, of course, we have the oxide. All right, so that is the base name. Okay, and now let me do this. You can see how we're working this here. This first column is the base name. Okay. Here's the base name, first one, bromine oxide, phosphorus. Oh, misspelled it. H. Okay, and now sulfur oxide, and then go back and add the prefixes, and you end up with sulfur trioxide. Okay. Nasty smelling gas. Some cars, some vehicles have this as an exhaust. So you ever get behind it, you smell like a rotten egg. It smells like a rotten egg smell. That's what you're smelling. Okay. Here, they're giving you the name. Now they want you to write the formula. Okay. So you work it backwards. And the first, when you were given the formula, we wrote the base name here. So here we write the base formula. Okay, so the base formula will be iodine. It says iodine by itself, and then fluoride. So IF, that's the base formula. Okay, and then you go back and check the prefixes. And it's 1 iodine and 6 fluorides. So you end up with IF. 6. Okay. All right, here's another one. Dichlorine pentoxide. Dichlorine. So we write the base formula. Okay, notice chlorine, that's telling you that Cl is in the center, and then oxide, pentoxide. So there's the base formula. Go back and add the prefixes. There's 2 chlorides and 5 oxides. Okay. Here we have, oh, now they want you to do, now they give you the formula. So again, we go back to writing the base name, and we got a phosphorus sitting up front. So we got phosphorus and iodine, excuse me. Okay, as the base name. Okay, then go back and insert the prefixes, and we have 2 phosphorus, and there are 4 iodides. Okay, all right, so there you go. I don't. If you're given the formula, my suggestion is write the base name and then throw in the prefixes. If you're given the name, write the base formula and then put in the numbers afterwards based on the prefixes, okay? Whichever works for you until you're comfortable with it, with just looking at it and then writing the formula for covalent compounds. Again, covalent compounds, the only ones that require a prefix, okay? Not the ionics. All right, just a few reminders. Prefixes only for the covalent compounds, okay? Roman numerals only for those metals that have variable charge metals. And so that means anything other than the sweet 16 require Roman numerals. And if you don't know which Roman numeral you have, you always know what its partner's oxidation number is. So you can calculate what the metal oxidation number is, because you know that the total number of cations plus the total number of anions will always equal 0. Okay. And the names for the polyatomic ions, don't change the names. They are what they are given in the table. Okay. So I know sometimes it's tempted to say phosphorus tetraoxide. That'll be totally incorrect for that. Okay, that whole thing with a -3 polyatomic ion is called phosphate. And if you need 2 of them, it's still called phosphate, not diphosphate, it's phosphate. Okay. All right, so what do we got here? Why don't we very quickly, who wants to do the first one? What number 1? BACL, what would you call that? I guess they gave you the formula. What would be the name? I didn't break it up, so I won't give you the answers yet. I'll flip them out here in a second. How about somebody who wants number 1? Let me pull. I can, let me see what we got here. Who took it? Barium dichloride, not quite. Yeah, I mean, remember, barium, remember, is it ionic or covalent? There you go. Christina, you got it. Remember, the ionic compounds do not use prefixes. This is an ionic compound. Okay, so barium chloride would be correct. All right, how about the second one, NO2? Who wants that one? Try that one, Kathleen. Nitrogen oxide, 50% correct. Okay. Dioxide. There you go. You got your prefixes turned around. It's okay. Prefixes. So for ionic compounds, no prefixes. For covalent compounds, prefixes. It's okay. All right, number 3, a little bit more of a challenge. Okay, first identify ionic or a covalent. And so you can see you got a big old Fe there, which is iron, which means ionic. All right. Second of all, Fe, is it part of the 16? No, it's not. So therefore, that tells you I need Roman numerals. But I need to know which Roman numerals I need to use. Well, that brings me to the parentheses. The parentheses tells you polyatomic ion. Okay, so you go to your table and you look for a PO4. And you'll see that the PO4 has a -3 charge. Okay. So this has a -3 charge. And there's 2 of them. So that means that I got, what must this iron be? Iron 2, exactly. Okay, because this must be iron 2, because that gives me a total of +6 charges, and the phosphate gives me a total of -6. Okay, so it's a +2. Another, and that's correct, Leah. That would be the name, iron 2 phosphate. And if you don't see it right away, another little tidbit, guess what? Look at that. That 2 represents the charge of that iron. So that would be correct, iron 2 phosphate. Now the formula for diiodine tetroxide, well, the base name or formula is simply the I and the O. The di means I got 2 of them, and the tetra means I got 4 of them. So it'll be I2O4. Okay. Sulfate. Who wants to take that one? Number 5, silver sulfate. Yep, silver. Not quite, Catalina. It's a good shot though. Remember, look at the key right here. Look at that. ATE. Yours would be IDE, sulfide. Okay. No, not quite, Kathleen. What is the ATE? Remember there is the sulfide, sulfate, and sulfite. Okay, the 8 and the I deal with oxygen. The IDE is all by itself. There you go. There'll be the SO4. Okay. And so that'll be correct. The Ag2SO4 would be correct. Now the SO3, Alexandra, the SO3 will be the I. So this one, the 8 will be SO4 -2, and the I will be SO3 -2. Got it. Okay. Now, compared to, guess what? Look at here, IDE. Okay, now we're dealing with the sulfur all by itself. And then we're dealing with nickel 3. So that would be nickel +3 and -2 for the sulfite. So we got 2 dissimilar charges. We got to put them together, and we just find a common number, which is 6. That means I need 2 nickels and 3 sulfites. Okay. Let me clear my mess, and we'll give you the answers there. Okay. All right. Well, on the web course, there is a worksheet that deals with this chapter. My suggestion, strongly do it, okay? Because it will help you out. Also, let me make sure. Okay. Uh-oh, where'd it go? Where'd it go? I lost my. There we go. All right. So also do that chapter, and congratulations, we're done with chapter 8. Okay, what I wanted to do is to remind you, let me make sure I pull that up correctly, is to remind you about the study mate that's on the website. So if you go to the Canvas website, on the left links, in the far left links, you'll see study mate. Okay. If you click that, oh, I can't, I'm logged out. If I click study mates, it sends me to this page. Now up here is a nomenclature practice setup. There's 143, I mentioned this before. There's 143 formulas and names. Now, what works good is the flashcard and matching. The other ones kind of work okay because unfortunately the study mate doesn't recognize like parentheses, but flashcards are good. So you click up a flashcard, there's 143 compounds and formulas here. So for example, you got boron trifluoride. That is the name. It wants you to figure out the formula. You flip it over. There you go. It's a B after you remember that this doesn't support subscript. So that's a subscript 3. And then you go on to the next one. There's chromium 6 iodine. Flip it over. There you go. Okay. So that kind of helps you. There's 146. Now, as you go along, remember, you can mix and match the cation and the anion. And if you think about it, you have roughly about 20,000 different combinations just in this 143 setup here. Okay, so you can, like right here is chromium iodine, but you could have done chromium fluoride. You see what I'm saying? So on and so forth. Now, the other one that works pretty good, I kind of like, is the matching. And so you have a name here, in this case, diiodine heptoxide. Okay, so you look for the formula. Okay, we got iodine and oxide. So it's I-O. And so here's I-O only. So you can't be the others. And then it says diiodine. So that's consistent. And then hep at 7. So boom, there it is. I got it. Okay, otherwise it would, if I click a wrong answer, let's say click this one, it says, no, it's wrong. Okay, so that's another, that's a good question. It's been a while since I looked in there. The nomenclature, let me look and I'll send an email whether it's multiple choice or not. Now, the thing about it, some people were, one more question. Okay, I'll find out. It's been a while since we put that in there, but I'll check it. Some people, let me explain why I put the 0 in that grade, okay? And this is based on my experience teaching at GCC, now at SCC. SCC has a special requirement. The department requires this nomenclature exam. Some other departments require something else, but for SCC, it's a nomenclature exam, and they require. It used to be it was do or die for the whole class, and we argued the point that no, if you're doing, you're doing an A, why should you flunk a course just because you can't answer 20 questions concerning nomenclature? Long story short, it is compromised, so it's worth 10% of your grade. Now, if you don't pass it, does not mean you won't pass the course. But if you're on the border of one of the levels, A, B, C, D, so forth, it can knock you down the whole grade. If you're up in the high A's, 10% probably won't have that much in effect. But if you're on the border, lower A, it can drop you to B. Same thing all the way down the road. You go from C to D, D to an F. Okay, so in the past, some people have not taken it, and you end up with a 0 and pass the course. And that's what they want. That's fine. But what used to be done is we would say, okay, here's a due date, which is normally toward the end of the semester, and people waited pretty much like a couple of weeks before the end of the semester before trying it. And when they didn't pass it, he ended a 0. And so it really affected the grade. So they were kind of quite upset. My grade, what can I do to get my grade back up? Well, I don't know what to tell you. You had all semester that you have an unlimited number of attempts, and you can continue to try it over and over again. And I have some people have tried up to 60 times because they wanted a perfect grade, but they kept hitting like 90%. Anyway, and so you have multiple attempts. It really doesn't have a due date per se, but it does have a last day of attempt, which is on the 14th. And so from this point to the 19th, you can go in there and try it ending multiple times. There's 20 questions. You just need 80% to pass it. If you don't get an 80%, then I have to move whatever you got, put it to 0. Okay. So if you're happy with 80, then we leave it there. If not, you can continue to attempt it if you want to get up to your 100% and get points that way. It's totally up to you. So would you flunk the course if you don't take it? No. Okay. But it depends on where you're at grade-wise. And so that's why I put that 0 in there now, because Canvas only shows you the grades that have been graded. So it's not really a true picture of where you're at until everything's been graded, right? So to give you a picture of what effect it has, I put it in a 0, and you saw how the grades dropped. And it doesn't mean that's where you're going to be at. No, because you're doing new assignments, and that grade's going to go back up. But still, they demonstrated the effect of not doing that. What can happen if you just let it sit there at a 0? Okay, so that's the reason behind that, because I didn't want to wait for the end of the semester and you got 1 or 2 weeks and you're freaking out. What can I do to improve it? I don't know what to tell you. You need to practice and try it throughout the semester. So we finish your nomenclature. You got a better feel for everything we covered here. Probably will get you at the 80% level with no problem. Okay. And that's why I said throughout the time you can mix and match it. Just because we talked about one particular compound, just be aware that you can move it around. Instead of all chlorides, you can throw in the iodides or any of the polyatomic ions. And, right now you have access close to 20,000 different compounds, quite a bit. Anyway, so that's the reason behind that. So, yes. Yeah, multiple attempts is that for that exam, you can do it as many times as you want, and Canvas will keep your highest score. Okay, and if it's lower than 80%, then I need to put it to 0. Canvas can't do that. I can do that manually. All right, that's true. You can also click on 0 to give you a grade for your choice to gauge. That's true. Canvas does allow you to give you a what-if situations. Okay. Any other questions or comments or concerns? What I want to do is there was, let me pull this up real quick. I sent you can't find it. There it is. All right, 2 things. Okay, and then I'm going to do the other one. Okay, this one dealt with polyatomic ions. Let me share this. And I sent you a Word document and a PowerPoint. Okay. In the Word document, this deals with polyoxy anions, the nomenclature, because you're going to find some of these in the nomenclature exam. And these are things like in the polyatomic ions, you had the sulfate and the sulfite, and the nitrate and the nitrite. Well, those are the most common polyatomic ions with respect to anions, polyoxy anions. But there are others, okay? And so the Word document kind of breaks it down for you. It starts off with what we call the base polyatomic ion, oxy ion. Now, the ones in yellow, those, you got silicon, tan, GE, stannous, and so forth. The ones in yellow all have 4 oxygens, okay? And they also have the corresponding, you see the sulfate, the SO4, they also have the corresponding charge, -2 for the sulfate and down all the way down to group 6, okay? The phosphate, -3, and the silicon oxide, -4. The ones in blue only have 3 carbons. They start off at 3 carbons. What this is the base name is the 8. All of them share the ATE ending, okay? So the ones in blue with boron, carbon, and nitrogen only have 3 oxygens attached to them. Then they also have the corresponding charge. The BO3 has a -3, the carbonate has a -2, the nitrate has a -1, okay? All right, now the ones in green, there are some halogens that will react and combine with oxygen to also form these polyoxy oxides. So chloride, the ones in green, all of them can only combine with 3 oxygens, and all of them have a -3 charge. So ClO3 has a -1, BrO3 has a -1, and IO3 has a -1, okay? Now, all of them, the blue, the yellow, and the green, that structure, what they share is the suffix 8, ATE. So for example, CO3 -2 is carbonate, okay? The NO3 -1 is the nitrate. And then we got the borate, the silicon, and the silicon 8, phosphate, so on and so forth, sulfate, all right? So that's how that works. That is the base name. Now, what can happen is we can, when we remove oxygens or add oxygens, we change the name. So if you start, for example, the rules, if we start with number 3, we're going to use carbonate as an example. Carbonate is right up here in blue, CO3 -2, okay, that's carbon, okay? This is the periodic table that we started off with, okay? We're not using the oxygen or the fluoride, but all the other elements just in this section of the periodic table. That's it. They're the only ones that create these polyoxy ion oxides, okay? And so we take carbonate, CO3 -2, and that is the base formula. Now, starting with number 3, base formula, that's the name. If it removes an oxygen, we go to 2, and we change the name to carbonate, okay? Just like sulfate had 4, and we went to 3 oxygens, so we removed an oxygen, it becomes sulfite, okay? Now, it is also feasible, depending on how many oxygens, to remove 1 more oxygen, which is number 1, which we have removed 2 oxygens from the base formula number 3 here. So that name now goes to, we add that prefix hypocarbonate, okay? So from the base formula, it's also feasible to add oxygen. So to go to CO4, -2, and so that name becomes percarbonate. So the base name, which will be the name for all the ones we just have here, that is the base name there. And they can either remove the oxygens, 2, or add 1. And so we end up putting the prefixes. So the formula for 1, 2, 3, and 4 oxygens, the base is carbonate. Okay. Remove 1 oxygen, it becomes carbonate. 2 oxygens becomes hypocarbonate. Adding an oxygen, CO4, gives you percarbonate. Okay. And these are the base names there. We got the carbonate, boronate, the nitrate, orthosilicate, germanate, stannate, etc., etc. Those are for the elements there. Hold on 1 second. Give me 3 minutes. Okay, I'm back. Sorry about that. And so let me rehash real quickly. This is only for what we call polyoxy anions, okay? And we only start off with these elements listed here: the boron, carbon, nitrogen, and silicon, uranium, and stannous, and so forth. Those are the only ones that we're aware of that create polyoxy anions, okay? So if all of these were the single element, just a single element, and they gain or lost electrons, for example, nitrogen, we know when it gains 3 electrons, it becomes nitride, okay? Carbon can gain electrons too, or lose them, but if it gains electrons, it becomes carbonate. All right, so on. But they all of these can gain or lose electrons, and we change the name to the IDE. Okay. Now, they will also make these oxides, polyoxide anions. And so what we did was we broke it down here for you. There's a couple of links here that you're more than welcome to view. There are YouTube, some other chemists have YouTube describing how they did this, how this is done, how this table works. So feel free, obviously, to go up there and watch these videos. And so what the bottom line is this: the ones in blue only have 3 oxygens. Okay. When we talk about the base name, the base oxides. So the boron, its base one is 3 oxygens, carbon 3 oxygens, and nitrogen 3 oxygens. The ones in yellow, everybody in yellow, their base starts off with 4 oxygens. And the halogens, fluorine, bromine, and iodine, their base starts with 3 oxygens. Now, we also list the respective charge on them. And so group the sulfur group 6 has a -2 charge. Group 5, they have a -3 charge, and group 4 have a -4 charge. Okay. You see how that works? So everybody in yellow has their corresponding charge, and they all have 4. From this point, they can either lose or gain electrons. And we're going to only take it to either gaining 1 and lose it up to 2 electrons. And so we use the example of carbonate. So carbonate has the formula CO3 - 2. That's its name of parentheses, carbonate. When it loses 1 electron to create what's called the CO2 - 2, that is called carbonate. And if it loses 1 more electron, oxygen, excuse me, it has a formula of CO -2. The charge doesn't change, just the number of oxygens. Losing 2 electrons, now we put the prefix hypocarbonate. If it picks up 1 oxygen, then it has 4. Started off with 3, now has 4. Then we keep the name carbonate, but we put the prefix percarbonate. Okay, and then that table gives you the name of each of the resulting polyoxides. And normally we're dealing with the ite and the ate, but occasionally it could be the hypoite or it could be the perate. Okay, those are the base names that you start off with, and then you start losing. See, here's carbonate sitting up there. That's the base name. That's with three oxygens, and then you can lose it. You can substitute any of these in that table, and you will find you'll have its corresponding name. Okay, and this is just extra examples there. I mean, you can use to help you out to figure out how to set it up. Okay, by viewing the videos. I also created this PowerPoint slide. Okay, where you start off with the respective element. We're not using oxygen and fluoride. Okay, it's just boron, carbon, nitrogen, so forth. All right, and so that is the corresponding charge that the polyoxides will have. Okay, starting with the nitrogen, we're going to end up with a -1 overall, -2 for the carbon based, and the one with the boron based. Okay, and so the base name, the ones in blue only start off with 3 oxygens. The ones in yellow all start off with 4 oxygens. And the ones in green start off with 3 oxygen. That is the parent name, if you will. And then we go from there, either losing or gaining I keep saying electrons, losing or gaining oxygens. And we change the name accordingly. But the charge for the polyoxy anions still remains the same, okay? We don't change the charge. It's still, like, for example, the carbonate, all remain -2. The only thing that changes is the number of oxygens and their respective name. Okay? All right. I'll let you digest that for a bit and look at the videos and so forth, because that would help you out with respect to naming some of the compounds. Probably about 10 to 15% of the nomenclature examples that utilize the polyoxy ions, anions, I should say. But by and large, everything we talked about, the study mate, that will cover more than 80% of the compounds that you'll be dealing with. Yeah, you're able to print that. You can print that out. It's PDF file. Yeah, it's PDF file, and the other is a PowerPoint. If you have Microsoft PowerPoint, you should be able to pull that up and skim through like you have a PowerPoint. or you can use, I believe, Google's tools to help you out. Okay. And if the PowerPoint doesn't work for you, let me know and I'll convert it to a PDF. But you can, it's a lot better. You can make it work as a PowerPoint because by clicking it, you can see the changes of the number of oxygens and the charges and so forth. Okay, no problem. All right, so what we have here is chapter 9. I'm debating, I think, I'm giving you a lot of information here. I think I'm going to stop it here. And I know you have the final in the lab today and the exam tomorrow. So why don't we wait on this? Yes, the question was the 2 slides I sent you. Yes, I did. I did send them email. And what I'll do, let me see if it allows me to send it here. Give me a second. I'm having a little bit of a challenge. Okay, I think I can send you a couple of files. If you want them, I'm gonna send you that. This, okay, I'm gonna send you the PowerPoint. That one. And that one. And that one. Okay, so I sent you 3 files, but I did send them through email. I think the last one I did not send, the nomenclature of acids. I'll remember, I'll send that through email too. There's another file that kind of helps you with naming acids, okay? And these polyatomic anions are related to the acids. The ones with negative charge, and when you put a proton back there. Yeah, the Canvas email. Everything I send, remember, I send stuff through Canvas. Our official method of communication is through Canvas. So it's in Canvas. So you may want to check your Canvas email. If you set that up, it will alert you to your regular Maricopa email. But I think they're all hooked up. So, okay. All right. Well, I'm going to stop